Hello. I am a Canadian person, and here's a photo of our good-looking Prime Minister. Not this guy, and also not her. It's this guy, Justin Trudeau. Here's another photo of him. So one time, like 6 or 7 years ago, he was at a preface conference. It's taking place at this Perimeter Institute, which is in Southern Ontario. It explains all the equations on the back. It's a place where they do research in quantum physics and quantum computing. And it was actually just a regular press conference. He was, answering questions, and I'll play a little clip for you. The first thing you're going to hear is an off-screen reporter asking him a question about foreign policy.
I was going to ask you to explain quantum computing, but when do you expect Canada's ISIL mission to begin again? And are we not doing anything in the interim while we prepare?
Okay. Very simply, normal computers work by... No, don't interrupt me. When you walk out of here, you will know more. Well, no, some of you will know far less about quantum computing, but most of you, normal computers work either there's power going through a wire or not. It's 1 or a 0. They're binary systems. What quantum states allow for is much more complex information to be encoded into a single bit. Regular computer bit is either a 1 or a 0, on or off. A quantum state can be much more complex than that because, as we know, things can be both particle and wave at the same times, and the uncertainty around quantum states allows us to encode more information into a much smaller computer. So that's what's exciting about quantum computing, and that's what we're looking at. Don't get me going on this, or we'll be here all day, trust me.
All right, not too bad. Not a terrible explanation. I'll give you a B plus, Mr. Prime Minister. I do have all day, and I love quantum computing, so I'm here to tell you a little bit about it. Okay, so as the Prime Minister said, if you have a normal computer or a classical computer, classical really always just means not quantum. So if you have a normal computer, it operates with bits, and bits are a logical concept. It's an abstract concept, 0 or 1. But your computer is a physical device, so you need some physical objects which encode or store these logical bits. So, as suggested, a common way is to maybe have a wire which has some voltage on it, and maybe a low voltage will stand for 0, and a high voltage will stand for the logical concept of 1. On your hard drive, you have a hard drive with millions of potentially magnetized regions, billions perhaps. And maybe you can have an unmagnetized region stand for 0, or a magnetized region stand for 1. Okay, so this is how you can store logical bits with physical devices. Of course, you need to read out what, as you're doing your computing, read out what these physical objects are storing. So you need some kind of measurement that takes the physical object and turns it back into a logical bit for you. So for example, if you're using the voltage on a wire, you might have a voltmeter, to apply to the wire, and it will read out for you whether the voltage is high or low, and you can think of that as you can find from that whether it's standing for a logical 0 or a logical 1. So this is called a measurement. Now, you might try to build your computer with smaller and smaller physical objects representing logical bits, and you could even try to get to the quantum scale and try to find some physical property of let's say even one subatomic particle that has 2 basic states that you could potentially use to encode 0 or 1. Actually, you'll notice here I've switched to writing 0 and 1 with these funny angle brackets. That's a quantum convention that I'll explain a bit about later, but for now they just mean, the logical 0 and 1. So for example, you might take an electron, and I can't draw an electron, so this is some representation of electron. And one property electrons have is something called spin. And an electron might have the property spin up, or it might have spin down. These are 2 basic states the electron can be in. And you might say, great, I have these 2 basic states. I'll put an electron having spin up to mean 0, and an electron having spin down to mean 1. Another subatomic particle you could try to use to store a logical bit is a photon. And I like photons because, I can see them with my eyeballs, if there's 10 or 20 of them at least. And photons also have different physical properties, and one of the physical properties they have is called polarization. And 2 basic states that a photon can have are horizontally polarized or vertically polarized. And you can just say, great, I'll take a photon, and if it's horizontally polarized, that'll stand for 0, and if it's vertically polarized, that'll stand for 1. And I guess the cartoon of polarization is that, if your photon is traveling, if it's wiggling horizontally, That's horizontal polarization, and it can be wiggling vertically, and that's vertical polarization. Great, so this is how you might, two different ways, you might try to use a subatomic particle to store zeros and ones. Now again, it's not enough to store them. You have to like read out from the physical particle later a date whether it's storing a 0 or 1. So let's say you're trying to store a 0 or 1 with the spin property of electrons. Well, you can take your electron and measure it by putting it through some complicated physical device. I just stole this picture from Wikipedia. I guess you put the electron into this like big magnetized area, and if it's spin up, then when you pass it through, it'll like move in one direction, and if it's spin down, when you pass it through, it'll move in a different direction. And so you've actually kind of changed the property from spin up, spin down to a different kind of property, like whether the position is up here or down here. And then you can like furthermore detect where the electron was, and then thereby like measure or read out eventually whether you had spin up corresponding to 0 or spin down corresponding to 1. Okay, that's a little bit complicated. On the other hand, for the case of a photon, where you're using polarization to store 0 or 1, you don't need such a fancy device in order to measure the polarization of a photon. In fact, you can do it with a rather unfancy device that you can buy at your local optician, which is polarizing sunglasses. So these are some sunglasses that you can buy if you're doing a lot of highway driving, you want to cut down on glare. The lenses have the property that, whether or not a photon can pass through the lens depends on its polarization status in some way that I'll mention a little bit later. But and therefore like blocks some of the light, and this, cuts down on glare. In fact, you use exactly this phenomenon also in a common situation if you go to a 3D movie. So here's like a little picture of people watching a 3D movie, and you see how they have these funny glasses on. And the way this works is, the glasses have these polarizing lenses in them, which are just plastic with some special property. And they set it up so that one eye, the lens in one eye, only allows photons through the lens if they're, let's say, horizontally polarized. And in the other eye, you have a lens that only lets photons through if they're vertically polarized. And therefore, if you project an image, or rather if you project two images with different polarization, like one image with horizontally polarized photons and a slightly different image with vertically polarized photons, then these lenses set it up so that one eye can only see one image and the other eye can only see the other image, and therefore you can like see a 3D effect. Okay, so this is how you can use polarized photons in your everyday life to watch some cool 3D movies. And as I said, they give you these glasses when you go into the 3D movie. It's a very cheap device, this kind of lens. This is really just like a piece of plastic with some special properties. And you can, buy such pieces of plastic, these polarizing filters, or Polaroids, as these pieces of plastic are sometimes called. You can buy them at your favorite online retailer. This is not a paid promotion, but you see here, you get this square. This costs you $8, but actually it's a pack of 10. So each one of these like little squares you can buy for 80 cents. So I have them here. This is a polarizing filter. You can buy it for 80 cents. And you see, like, if you put it in front of the camera or the light, it actually blocks about half of the light. Okay, so cool. So for the rest of this presentation, I'm going to depict it not with the actual photo of the real-life image, but by this circle with the horizontal stripes. And this is going to represent a horizontal polarizing filter. So let me explain at a high level and an abstract level what this horizontal polarizing filter does, because in some sense it can be used to indirectly measure the polarization of photons. So this is a horizontal polarizing filter. And let's say you take a photon, and it's horizontally polarized. What happens when it hits the filter? Well, I'll just tell you, what happens when it hits the filter is it passes through. No problem. It's as if it were transparent. On the other hand, you can take a photon which is vertically polarized, and what happens when you pass a vertically polarized photon through a horizontal filter? What happens is it gets blocked. So I don't know the exact chemical properties or physics properties of it, but the upshot is vertically polarized photon, when it hits the filter, does not pass through, and in fact, furthermore, like somehow it gets transformed into a tiny little bit of heat. Okay, so you can use a horizontal filter in some sense to detect whether a photon is horizontally polarized or vertically polarized. You can just see if it passes through or not. Or conversely, if it like heats up the filter a little bit. Now, you can also similarly get a vertically polarized filter, which you need one of each in order to make the 3D glasses. And in fact, you don't have to buy a different special kind of filter. You can make a vertically polarizing filter just by taking your horizontal polarizing filter and rotating it 90 degrees. And now it's a vertically polarized filter. So it has the same, the analogous properties. If you have a vertically polarizing filter, you take a vertically polarized photon and pass it through, then it just, passes through. But if you take a horizontally polarized photon and pass it through the vertical filter, then it gets blocked. And, the filter like heats up a tiny little bit. Okay, cool. So, in fact, you can do like some cool experiments with these little things. I'm not going to talk about this too much in this presentation, but if you take like a horizontal filter and you shine some light through it, then about 50% of the light gets through. And roughly speaking, you can see it's a little bit grayer there. Roughly speaking, it's because, you could imagine that like half the photons are horizontal and half of them are vertical. And so like only 50% of them pass through. That's not quite right, but it's something like that. One cool thing is actually, like once light shines through the horizontally polarized filter, any photons that do pass through are all horizontally polarized. And then you can do like a bit of a neat trick. You see, you can put a vertically polarized filter behind it. And now, since you know that all the photons that made it through the horizontal filter are horizontally polarized, you know that they'll all be blocked by the vertical filter. Okay, and therefore, like, no light should get through. So let me see if I can do this. It depends here. Yeah, so here's like a horizontally polarized filter, and half the light is getting through. And I got this one, and I turned it, so like now, like, oh, you see, like, no light gets through. Zero intensity. On the other hand, if I like rotate this one to also make it horizontal, then it's kind of like nothing happens. So basically, you don't see any difference if I put two of them in a row. But if I put like horizontal and vertical, then it blocks all the light. Actually, I cannot help but mentioning like another cool party trick you can do, which is this. I won't explain this, but you should be able to reason about why this is true by the end of this presentation. A filter cannot be just like horizontal or vertical, but you could make it, let's say 45 degrees. And guess what happens if you put like this in between the two filters? I don't know if you can easily see this. It's all black, but if you put it's not so easy to tell. Let's see if I can do this well. Okay, we have horizontal and vertical. It's like all black. And now I'm going to interpose one diagonally. And like, oh, you see, you can now see through it a little bit. You can see my face a little bit. If I take it out, it's pretty much black. Put it in, you can see a little bit. Yeah, it's a cool party trick. As I said, I'm not going to explain why this works. It seems counterintuitive because with just the horizontal and the vertical filter together, all the light was blocked. So you'd think that like, oh, if I further interpose another object, like it can only be more blocked, right? I mean, how could like adding some kind of barrier increase the amount of light that comes through? But this is exactly what happens. It's kind of awesome. And yeah, maybe by the end of this presentation, you can go back to this part and try to reason about why this is the case. Okay, so that's like a little party trick you can do. But I want to talk a little bit more about, photon polarization and measurements and so forth. So this polarizing filter, I don't think of it as like conceptually the best way to imagine measuring the polarity of light. You can actually build another device, which is maybe just a polarization measuring device that will just sort of directly tell you whether a photon is horizontally or vertically polarized. Now, it doesn't look like this in real life. But just for this purposes of this presentation, I've depicted it as like a camera, like attached to an LCD readout screen. Okay, so this is my abstract hypothetical polarization measuring device. And how does this work? You take let's say you have a horizontally polarized photon and you put it into the measuring device, then it just reads out 0 on the LCD screen. Okay, so we decided that horizontal is going to correspond to 0. On the other hand, if you take a vertically polarized filter and pass it into this device, this polarization measure device will read out 1 on its LCD screen. Okay, so you put in horizontal or vertical into this device, and it just reads out on its screen whether it's 0 or 1. So this is like kind of like a clean polarization measuring device we could imagine. And I'm a computer scientist, so I actually kind of think about this in terms of like, I've written it here as kind of like an abstract, function that you might call in some computer code, just like a measurement operation that you can do to a physical photon that'll read out 0 or 1 for you. And I actually think of like the horizontal filters as kind of like a measuring device plus like a little bit of an if-then statement afterwards. So the way I think of, you might imagine a horizontal filter in this code is like this. So the horizontal filter takes in a bit and it applies, you can imagine it like hypothetically applies this perfect measuring device that reads out either 0 or 1. And then it has this extra feature that if the readout is 0, meaning horizontal, then it returns the bit to you. It like passes it through. And on the other hand, if the readout is 1, then it doesn't return you the bit and it just generates heat. Okay, so I have some fictional programming language here that sort of describes abstractly what a horizontal filter does in terms of like a perfect measuring device plus this little if-then that either gives you the bit back if it's horizontal or it gives you heat if it's vertical. Okay, and then you could also have a similar such code for a vertical filter. Now I put this object up on the screen because if you're building, let's say you're trying to build a computer out of tiny subatomic particles and maybe using polarization to store 0 or 1. It's not that you just like try to store bits and read them out again. You also need to manipulate bits. So you might wish to, let's say, transform a 0 into a 1. So you need some physical mechanism that takes your horizontally polarized photon, which stands for 0, and transforms it into a vertically polarized photon, which stands for 1. And you can, at least in principle, get this by another very like lowbrow, simple device, like a slab of crystal, like apparently quartz can do a good job. So you take a nice slab of quartz like this, and this can, in some sense, abstractly implement the NOT operation, the logical NOT operation. If you get the thickness of the quartz just right, then it'll have the following property. If you take a horizontally polarized photon and you pass it through the quartz, then that will like change its polarization to vertically polarized. Okay, and this way you can have like a NOT operation on your qubits or on your bits, and therefore you can try to start manipulating bits and maybe building a computing device out of it. Now, you can't really do interesting computation with just one bit. I mean, if you tried to imagine building a computer with a bit, you could store a 0, store a 1. Maybe you could apply a NOT gate to it to flip it around. This is not really enough to do interesting computation. But it turns out you can kind of do some interesting computation with just one qubit with these subatomic particles that have properties like polarization. And this is what I really want to tell you about in this presentation, how you can do something that looks like a kind of intriguing algorithm already just using a single bit stored by like a quantum particle. So in order to explain this a little bit better, I've noticed here, you might notice here, I took this depiction of our NOT gate, which is a slab of quartz, and I said like, oh, if you just, make this slab of quartz the right thickness, it'll operate like a NOT gate. It'll turn horizontal polarization into vertical polarization. This is all happening in the real world. You could say, like, what if I don't get the thickness right? In fact, you might ask, like, what if I take this slab of quartz and like make it only half as thick? Okay, so then what happens? I could still build this piece of quartz, and I could still like try to pass photons through it. Like, what does it do? Well, it turns out it does something kind of interesting. If you take a horizontally polarized photon and you pass it through the half thick piece of quartz, let's say, then it gets into a new polarization state, which is neither horizontal nor vertical, but it's this diagonal kind of looking state, which you might describe as some kind of combination or superposition of horizontal and vertical. And now this is exactly like what the Prime Minister was talking about. We have here a qubit, it's called, and its state does not correspond to either 0 or 1, but being sort of halfway between 0, what we're calling 0 and 1, we kind of have like a physical object that's representing something that's an equal superposition of 0 and 1. And this is another nice thing I like about photons and polarization for thinking about quantum and qubits. It might seem a little bit weird to imagine, oh, like my electron is got like some superposition of spin up, spin down. I don't really know what spin means, so maybe, but like it seems also weird if like your electron has a equal superposition of being up here or being down here. That seems very mysterious. But if I just tell you, okay, we have polarization of a photon and it's an equal superposition of horizontal and vertical, it's kind of like diagonal, that seems less crazy. So let's talk about the notion of a qubit. So in fact, if you're storing, information with, let's say, one photon's polarization state, the most general state it can be in is like some kind of amount x on logical 0 and some kind of amount y on logical 1. These amounts are sometimes called amplitudes. And in fact, it's physically possible for the amount of 0 and the amount of y, the amount of 1, x and y, to be any real numbers, x and y, subject to one condition, that x squared plus y squared equals 1. So there's actually really only one degree of freedom here, because essentially once you choose the amount x, the amount y is more or less forced up to its sign, because x squared plus y squared has to equal 1. But you still have like infinitely many possibilities for like how much amount of 0, and therefore how much amount of 1. Actually, if you really want to get into the details, technically speaking, these amounts, x and y, can even be complex numbers, but I put it in teeny tiny font because we're not going to actually need to worry about complex numbers in this presentation. So it's fine to just imagine that these amounts, the amount of 0 you have and the amount of 1 you have, are real numbers. Okay, so for example, let's take a look at this hypothetical qubit, which is an equal superposition of 0 horizontal and 1 vertical. So the two amounts, x and y, are supposed to be the same because it's an equal superposition, but we also know that x squared plus y squared equals 1. So that just means like x and y are going to both be the square root of a half. So the way mathematically you represent this qubit state is square root of a half amount on 0 and square root of a half amount on 1. Or if you're being fancy, you call these square root of half amplitude on 0 and square root of half amplitude on 1. So in fact, geometrically, it's nice to think about the state of one, let's say, photon's polarization, or one qubit, as a point or a vector in the two-dimensional plane. So here's a little plot of the two-dimensional plane. We have an x-axis and a y-axis. And actually, this is the equation of a circle. X squared plus y squared equals 1. It's all the points on this unit circle of radius 1. And for each point, or each vector on the unit circle, such as this one, x equals 0.8, y equals 0.6, that corresponds to a possible state of a single qubit. Okay, so this 0.8 squared plus 0.6 squared is 0.64 plus 0.36, which is 1, so great. And it means it's possible for let's say, a photon's polarization state to be 0.8 amount on 0 and 0.6 amount on 1. You can picture this as sort of pointing in this direction here. It's also possible to, I just realized I was not gesturing with my mouse, but you couldn't see it. Well, hopefully I'll fix that now. Anyway, you can also represent this state as, in this way, write it in this way, 0.8 amount on 0 plus 0.6 amount on 1. And in fact, this is actually a correct mathematical way to write it under a certain nice interpretation. You see, plain horizontal polarization, which before we were denoting by 0 in these funny brackets, this just corresponds to x equals 1, y equals 0, like you have your whole 1 amount on 0 and your 0 amount on 1. Okay, and the previous notion of purely vertically polarized, which we denoted by 1 in these funny angle brackets, this just corresponds to x equals 0 and y equals 1, like you have your whole amount on 1 in these angle brackets. And in fact, mathematically speaking, this funny symbol 0 in these angle brackets actually literally just stands for this vector 1, 0. this unit basis vector. And 1 in these funny angle brackets actually just stands for this vertical basis vector, 0, 1. And then this, this yellow vector here really is 0.8 times this 1, 0 vector plus 0.6 times this 0, 1 vector. So in fact, this is a mathematical notation that makes sense, where every qubit state is represented by a vector, a point x comma y, where x squared plus y squared equals 1. Okay. So one thing we can imagine we can do is like take a qubit and sort of initialize it to the 0 state. So all of our amount on 0 and no amount on 1. So all of it on vertical. And one thing you might wonder about now is what happens when we pass it through. I mentioned that if you pass it through a slab of quartz at a certain thickness, it could rotate it by 45 degrees, rotate its state by 45 degrees. And in general, at least in principle, if you're doing these things carefully, the different thicknesses of the slabs correspond to different angles. And by making a certain thickness, you can make a physical device which will rotate the vector representing the polarization of the qubit by any fixed amount. So if you make it a certain thickness, it'll correspond to a certain angle theta, and it'll have the physical property that when you put in a photon at any polarization state, which we now know can be sort of associated with a vector in 2 dimensions, it will transform the state of the photon. So its new polarization vector, if you will, is the rotated vector by the amount theta. So this is a little depiction of that. Now suppose we do this and we make a slab that corresponds to rotation by some theta. If we start with the qubit in the state, all amount 0, which was horizontal, the new state of the photon will be depicted by a vector whose angle is theta from the horizontal. And we can write that in coordinates. This is sort of the definition of cosine and sine. The horizontal amount here, the first coordinate of this vector is cosine theta, and the vertical amount here, the second coordinate of this yellow vector, is sine theta. Okay, so in this way, by choosing theta appropriately, you can transform a photon in a known polarization state, like horizontal, to your favorite one, and that lies on the circle. And if you rotate by theta, it's be cosine theta amount on 0 and sine theta amount on 1. Okay. Now that this is lets you know how you can in general manipulate the state of one quantum particle, you might have the following interesting question. Well, what happens if I take a photon whose polarization state or whose angle, theta, is not just purely horizontal or purely vertical, and I put it into a measuring device? Now, at first you might think, oh, maybe the measuring device will tell us what the angle theta is. But that's actually not the case. I've depicted this measuring device like this. You can imagine this LCD readout screen can only read out 0 and 1. It just has like 2 different kinds of segments, one showing 0 and one showing 1. So in fact, when you put a photon like this into a photon polarization measuring device, the screen will still read out either 0 or 1. So what's the deal? Well, the deal is the only kind of logical thing that you could imagine being the case really is the case. So this is a fact about the laws of quantum mechanics. They tell you that if you put a general qubit into a measuring device, it will still read out 0 or 1 on its little screen as before, according to these rules. So the probability the readout will show 0 is the square of x, the square of the amount of 0 in the original state. So, if our state was this one at angle theta, you could also say that's the square of cosine theta. And conversely, the probability that the readout will show 1 is like the square of the amount that the photon had on 1. So like y squared, or in this specific case of the angle theta, the square of sine theta. And let me just convince you or make you notice that this makes sense. So x and y, these 2 amounts, can actually be positive or negative potentially, but x squared and y squared are always positive, or at least non-negative. So it makes sense to say, oh, the probability of something is x squared or y squared, because that's positive. Oops, I advanced the slide there by mistake. But we also have this rule that x squared plus y squared is always 1 for any state. And so these two numbers, x squared and y squared, also add up to 1. So that means this is like totally sensible. Like these two probabilities are supposed to be, you know, mutually exclusive. Uh-oh. One of my children just ran through the room shouting about being chased by his brother. Well, old one-take Ryan, they call me. I'm just going to keep on going here. So the probability that the readout is 0 or 1 is determined by the amounts of amplitude on your state, x squared and y squared. Okay, hilarious. Okay, so you know, as I mentioned before, you can really do interesting computation with just one qubit. And what I want to tell you about in the rest of this video, now that you know like all the rules of you know, how you can manipulate one qubit state and what happens when you try to measure one qubit, I'll show you some cool trick you can do using just this knowledge about the rules for one qubit. Okay, and this you know, algorithm I want to tell you about in the main part of this video is called the Elitzur Vaidman Bomb algorithm. So Elitzur and Vaidman were two physicists that suggested a certain like cool experiment you could imagine doing with one qubit, and they dramatized it using a bomb in their story, like a real explodey bomb. And I'll tell you about it, but like I like to think about it more in terms of like an algorithm as opposed to a physics experiment. So I'll explain it to you in these like algorithmic terms. Okay, so here we go. This is the main content of the story. So there's a box. Imagine there is a box, and it's an opaque box that you cannot see into. And in fact, there's another little twist here. It has a little slit in one side. And in fact, if you spin it around, there's another slit on the other side. So this slit is just wide enough for one photon. So one photon could potentially pass through this box. Let's depict it a little bit more abstractly, and I've made it a little bit translucent so we can see inside it, but in the story, in the game that's about to transpire, it's an opaque box. Now, what you should imagine is some crazy, weird person has given you this box, and they promise you there's one of two scenarios. Scenario 1, possibility 1, is that the box is empty. There's nothing in it. So in particular, you pass like a photon through this box, it'll just come out the other slit at the other side. That's possibility 1. Possibility 2 is that there's a bomb in the box. Okay, and not just any old bomb, like a weirdly set up bomb. Ta-da, there's the bomb. This is like this crazy pink bomb. And you see it has a fuse, and this fuse is attached to one of these horizontal filters that we've talked about. Okay, and so it's got like a hair trigger fuse, so it's a crazy situation. Here's the situation of possibility 2. You imagine that the fuse is so sensitive that even the slightest amount of heat will cause it to explode. So in particular, if you pass, let's say, a horizontally polarized photon through this box, then okay, it'll just pass right through a horizontal filter and come out the other side. But if you pass a vertically polarized photon through this box, it'll get blocked by the horizontal filter, and remember that generates a teeny tiny amount of heat, and that will set off the bomb, and the bomb will explode. Okay, so here's the summary of that. When you put a photon in, remember, you could think of like a filter as like a combination of like a measuring device, plus it'll take like a little bit of action depending on whether it's like horizontal or vertical, the readout. So if the readout is horizontal, the photon just passes through the box. And if the readout is vertical, then the filter like makes a little heat and that sets off the bomb. Okay, so we can imagine like, you know, since I want to describe this as like an algorithm, we can imagine possibility 2 is corresponding to this code. So if we have some, we imagine we have like a function called mystery box. You put a qubit into it. And the way it works is, if there's a bomb, you know, first it measures the qubit and assigns that to readout. And if the readout is 0 or horizontal, then we just pass. In fact, the qubit just comes out. But if the readout is 1, then, you know, this function causes an explosion. Okay, so you can think of the box with the bomb in it as corresponding to this kind of computer code. And in fact, if the box is empty, it corresponds to very simple computer code that just takes in a qubit and does nothing with it. It just passes the qubit through. Okay, so to summarize, you imagine that your strange friend is giving you this box, and it's either empty or has a bomb, or you can think of it as either it implements mystery box, either it implements this code or this code, and you want to figure out, ideally, which one it is. Now, suppose, you don't know anything about quantum, and you just always store photons as horizontal or vertical, so every, qubit is either just purely a 0 or purely a 1. So if you use only like classical bits like this, then you're in big trouble here. You can't really do anything useful at all, and let me explain why. If you only have classical bits, the only way you can interact with this mystery box to try to figure out whether it has the bomb or not is to try to pass in a bit. So what happens if you pass in 0? Well, if you pass in 0, you basically get no information at all. So why is that? Well, if the box is empty, if you pass in a horizontal photon or pass in a 0, then it just comes out the other side as a 0, and so you get a 0 out. On the other hand, if the box contains the bomb, the exact same thing happens. If you put in a 0 to the bomb box, since that's horizontal, the measurement step will always read it out as 0, and so then no explosion will happen, and it'll just pass right through. So either way, the output of the box is just a horizontally polarized photon. So you get no information at all if you put in 0. On the other hand, if you put a 1 into the box, well, this is not a good idea. I mean, if you put a 1 into the empty box, then it comes out as a 1, or it comes out vertically polarized. But if you put a 1 into the mystery box when it has a bomb, then an explosion is certain. So you don't want to put 1s into the box, because you might explode. But if you only put 0s in, then you get no information. But if you have qubits, if you have the power of quantum, then you can do something much more interesting and cool. So let's take advantage of the fact that a qubit can be in a superposition of 0 or 1. So now actually, this is not going to be the final form of the algorithm. This is like a warm-up algorithm, or like a first thing you can try that does something somewhat cool, but it won't be the coolest. So this is, the algorithm we're going to do. So let's take a look at it and imagine like carrying it out physically. Okay, so the first step of the algorithm is to like take a qubit and initialize it to 0, or like make a photon that's horizontally polarized. So we'll do that. So it's depicted down here. It's our horizontally polarized photon. The next step of our little algorithm is to rotate its state by 45 degrees. Okay, so that'll make the state that's an equal superposition of 0 or 1, sort of 45-degree diagonal. I started using some like math talk here. We're going to use radians instead of degrees. So 45 degrees corresponds to pi over 4 radians. Okay, so we'll have a nice quartz slab of the appropriate thickness, such that when we pass the photon through it, now it's at 45 degrees. Okay, and now we put it into the mystery box. So let's think about what happens. So case 1, the box is empty. In that case, well, you put the photon into the mystery box and nothing happens. I mean, it goes in and then it comes out in its exact same state. Okay, so in the empty case, it'll come out of the box in this state, an equal superposition of 0 and 1, or otherwise at 45 degrees. Okay, now the next step of our algorithm is actually to do another rotation. So that means we'll get like another piece of quartz of an appropriate thickness here, and we'll rotate by another 45 degrees, or pi over 4 radians. And still imagining the box is empty, we will get into a situation now where we've rotated by 45 degrees twice, so the polarization state of the photon is purely vertical. Okay, the next step of our algorithm, line 6, is to put this qubit into a measuring device. So we'll get out the measuring device here, and we measure the photon. So in this case, since the photon coming in was purely vertical, we know that's like one amount of vertical, 1. We know there's a 1 squared or 100% chance that the readout on the LCD screen back here will be a 1. This is in the empty case. So now if we look back at the code, it says, okay, if the readout is 0, then do this, but it wasn't 0. The readout is 1. So our algorithm will finally print out inconclusive, which might look a little disappointing. It would have been great if our algorithm printed out like the box is empty. we would have sort of solved the problem. It merely prints out inconclusive. But it's not so bad. You see, if you look at the code only ever prints out bomb or inconclusive. So at least it didn't wrongly tell us that there was a bomb in there. Okay, so this is actually the physical apparatus corresponding to the whole algorithm. And we see that if the box happens to be empty, when we run this code, we'll always see the outcome inconclusive. 100% chance of that when the box is empty. Okay, so now let's imagine what happens in the other case when the bomb is inside the box. So we'll just go through the lines of the code in this case. Okay, so we'll go back to the beginning. So we initialize a qubit to 0 or horizontal, and then we rotate it by 45 degrees. Okay, and now it goes into the mystery box at a 45-degree angle. And now we have the bomb in the box. So it goes through the filter, the horizontal filter. And now you see there's a square root of half amount on horizontal and a square root of half amount on vertical. So the two probabilities, x squared and y squared, are half a half. So there's a 50% chance that the filter can measure it to be horizontal and a 50% chance that it will measure it to be vertical. So there is a 50% chance that it will get measured as vertical, and then these horizontal filters, in that case, generate a little heat, and we explode, which is bad, granted. But let's rewind time. Let's rewind time here to right before it hit the filter. And there's also a 50% chance that it will get measured to horizontal. And when the polarizing filter measures a horizontal, it just passes it through. And it comes out in the horizontal state. So in that case, there's a 50% chance we survive to line 5 of the code. And then let's see what happens for the rest of the code. The next step of the code rotates the photon by 45 degrees. And finally put it into the measuring device. And actually now a similar 50-50 chance ensues, because once again we have a 45-degree, qubit entering into a measuring device that reads out 0 or 1. So once again, there's a 50-50 chance of each outcome. Okay, so there's a 50% chance that the measuring device will, detect it as 1 and show a 1 on the screen. And you see by the code that in that case, we will again print out inconclusive, which is again maybe a little bit disappointing. But if we once again rewind time just before the measurement, I should say that, so overall, in this case where the box has a bomb, overall there's a 25% chance that this algorithm will print out inconclusive, because there's a 50% chance you'll explode and a 50% chance the qubit will make it out of the box. And then once it makes it out of the box, there's a further 50% chance the readout will be 1. So there's a 25% chance overall of printing inconclusive. Yeah, but as I said, if we rewind time to just before the measurement occurred, there's also a 50% chance that the measuring device will show a 0 on the LCD screen. In that case, our code will print out bomb. And actually, finally, something kind of cool has happened. There was a bomb, and this actually occurs overall with a 25% chance, because again, there's a 50% chance the qubit makes it through the box, and then a further 50% chance that the measuring device says 0 on its screen, which corresponds to printing bomb. Okay, so let me summarize everything we've learned so far about applying this algorithm in the two cases of the mystery box having a bomb and the mystery box being empty. So the summary is, when the box is empty, there's a 100% chance that our algorithm will print out inconclusive, which is kind of a bummer. When the box has the bomb in it, a real bummer is there's a 50% chance that we explode, which is definitely bad. But furthermore, there's a 25% chance that our algorithm will print inconclusive, which is also not so great. But there's a 25% chance that the algorithm will detect the bomb. It'll print out bomb. So we have not a bad scenario here. I mean, it's not terrible. We have a 25% chance of learning that the bomb is in the box. When the bomb really is in the box, we have a 25% chance of learning this fact and not exploding, which is something that we could not achieve if we only used classical bits, 0s and 1s, as the inputs to our box. So this is pretty cool. But in fact, with a more sophisticated algorithm, you can do something that's even much better. And this is the content of the Elitzur-Vaidman Bomb algorithm. So this was our old code, which gives us some stuff that we want. Let's put it down here because this is actually going to be our new code. Okay, so this is going to be the final version of our code, which does something even more cool for trying to detect this bomb. So let's take a look at this code as well. So we're going to imagine running this code again in two cases, one where the box is empty and one where the box has the bomb in it. So we'll, as before, start with the bomb case, or sorry, the empty case. So let's see. The very first thing that this algorithm does on line 1 here, it actually asks for an input from the user, or you, the experimenter, gets to choose a value for this parameter n, which you should think of as the safety level. So n is like a positive integer that you can choose, and we'll see the higher you choose n to be, the safer from explosions you are. Okay, so you choose some parameter n, and then the second line of the code initializes your qubit to the state 0. And, well, we'll get to this in a second. And the third line of code sets this parameter theta, that's just like a variable or a parameter theta, to be this quantity, 90 degrees divided by n. Okay, so pi over 2 is 90, pi over 2 radians is 90 degrees. So you also see the bigger the safety level n, the smaller this angle is. So if you take a really high safety level, this theta will just be a really tiny angle above 0. The previous code is a little bit similar to the case when capital N, the safety level, is 2. In that case, there was an angle of 90 degrees over 2, or 45 degrees involved, but now we're going to imagine much smaller angles. Okay, and this little piece of quartz here is going to depict the operation that rotates qubit states by this angle theta. Okay, so I suppose the larger the safety level is, the thinner this quartz will be. Okay, so in fact, the code also has a loop. After this sort of initialization, there is a loop that goes from 1 to n. And you see, actually, the larger the safety level is, the higher the number of iterations of the loop there are. So the longer, the actual more time this little experiment or algorithm takes. So let's see what happens in this code in the empty box case. In fact, in order to implement the loop, we're gonna, you see, as we go through the loop, we sort of rotate the qubit and then put it through the box, and then we repeat this. We rotate it and put it through the box. So whenever the photon comes out of the box, we need to get some mirrors here to like loop it back around physically to go back through the rotator and back through the box. So let's watch as that happens. Okay, so I suppose we should also say that the last step of the algorithm involves a readout or measuring device. We'll set up our little polarization measuring device here at the end. Okay, so in step 1 of the code, or when things start to actually happen, we've entered the loop for the first time, and we rotate the qubit by an amount theta once. So now the photon's polarization angle, if you will, is theta. Okay, and the next step is we pass it through the mystery box. So the box is empty in our imagining right now. We're considering this case, so it just comes out at angle theta, which is this like small amount. Okay, and we have a loop here, so we're going to do this n times. So we bounce it around to the beginning, and we come into the second iteration of the loop. And the second iteration of the loop rotates the polarization state by theta again. So maybe now it's at angle 2 theta, and it goes through the mystery box again. And since it's empty, it comes out at angle 2 theta, and we loop again, and rotate the state again, put it through the box again, loop again. I think maybe n is 5 in my little example here. We rotate it again, pass it through. Okay, and this will be the last iteration of the loop, the nth iteration. So we rotate it again, and it's exactly cooked up so that at the end of the loop, in this empty box case, the polarization will be exactly vertical. You see, because theta is 90 degrees divided by n, or pi over 2 radians divided by n, and we do this loop n times. So if we do n rotations by theta, the overall rotation is 90 degrees, or pi over 2 radians. So since it started out horizontal, it ends up vertical. Okay, so this is the last iteration of the loop, passes through the box, and then since the loop is ending, we like whip this last mirror out of the way. And finally, we go to step 9, which is putting it into the measuring device. And we know in this case, since it's a vertically polarized photon, there's a 100% chance that the measuring device reads out a 1 on its screen. And so if you look at the last statement of the code, if the readout is 0, print bomb, else print empty. So in this case, we're going to print empty with a 100% chance. Okay, so this is actually very nice. We've just seen that, whatever safety level you choose, n, if the box is empty and you do this experiment or run this code, then there's a 100% chance that the code at the end prints empty, which is correct. Wonderful. So now let's imagine what happens when the bomb is in the box. Okay, so we're going to imagine going through this loop again, but it's seeing what happens when the bomb is in the box. Okay, so we again initialize the qubit to 0, which means horizontally polarized. And the loop will, rotate it by theta. And then it gets inside the box at angle theta. And it passes through the filter. Now you see, especially if n is large, the safety level is large, this theta is a really small angle. So it's like almost horizontally polarized. And so therefore, when it passes through the filter, there's a very high chance, and we'll compute properly later, but let's just say at a high level here, there's a very high chance that the filter will measure it to be horizontal. You might imagine like the amount of horizontal is like 0.99 or some very large amount, so 0.99 squared is very close to 1. So there's a very high chance that it'll be measured to horizontal, meaning the bomb will not explode, and it'll come out of the box horizontally polarized. So again, let's imagine that this high chance happens. We'll calculate the probability of exploding at the end. But let's imagine the likely thing happens, and it passes through the box, and therefore comes out horizontally polarized. Now, this is actually different than what happens when the box is empty. Remember, when the box is empty, we started the photon at angle theta, and it comes out of the box also at angle theta. When the bomb is in the box, and we don't explode, it comes out at angle 0 at horizontal polarization. Now you might say, oh great, like when the box is empty, it comes out at angle theta, and when the box is got the bomb in and it comes out at angle 0 or horizontal, let's just check which of the two is the case, and we can tell if the box is got a bomb or is empty. But remember, there's like no way you can just sort of look at a photon and tell what its polarization state is, like what its angle is. The only thing you can do is put it into a measuring device if you want to learn something about it. And if you put the photon into a measuring device, like right after it comes out of the box the first time, well, you won't tell much of a difference. You see, when the bomb is in the box, if we were to measure it now, we would always see 0 on the screen. When the box is empty and it comes out at angle theta, well, that's also almost horizontal, so we would almost always see 0 on the screen if we were to measure it then. So this is why there's a loop in the algorithm. We're going to do a little bit more. Okay, so we just saw that if, on the first iteration of the loop, if it makes it through the box and we haven't exploded, then the polarization state is actually back to 0. So then the second and third and fourth, etc. iteration of the loop will look actually always the same. See, on the second iteration of the loop, we rotate it a little bit. It gets to be at angle theta, which is 90 degrees over n. We pass it through the box, and we measure it. There's a slim chance that we will explode at this juncture, but if we don't explode, then when it comes out of the box, it'll be horizontally polarized, and we can continue iterating through the loop. Okay, and so every time it comes out of the box in the bomb case, if we haven't exploded, it's horizontal. So in the last iteration of the loop, let's assume we got through all the iterations of the loop without exploding. Last iteration of the loop, we pull the last mirror away and we move on to the final step of the algorithm, which is to measure it. And in this case, since it was horizontal, there's a 100% chance the measuring device will measure it out to be 0. And then line 10 of our code says if the readout is 0, you'll print bomb. So this is also great because you see what we've found here by analyzing the algorithm is if we make it all the way to the end of the algorithm without exploding, then there is a 100% chance the code will output bomb, which is correct. Okay, so in fact our algorithm is sort of always correct. When it is empty, when the box is empty, the algorithm will always print empty. And the box has the bomb in it, There is some chance that we'll explode, which I'm going to analyze soon. But if we don't explode, then we get a correct answer, 100% correct answer. We get the printout of bomb. So this is the summary, and this is like the cool aspect of the algorithm. If the box is empty, we have a 100% chance of detecting that it's empty. If the box has the bomb, we have a 100% chance of detecting the bomb, assuming we don't explode. So the last thing we have to worry about is like, what is the chance that we explode? And hopefully it's very small. Now, this is a funny question because there's a couple of things you might think about. You might think, okay, well, we have this safety level n, and our angle theta is 90 degrees over n, or pi over 2 over n, which is very small. So that's good. It's a very small angle. So like when you pass it through the horizontal filter, there's a very small chance you explode. And the chance gets smaller and smaller the bigger n is. On the other hand, the bigger n is, the more times you do the loop. So like the more times you have a chance of exploding. So it might not be obvious, like whether it's better to make n big or small, or maybe it doesn't matter. So we'll have to see. Because there are these two competing interests. The bigger n is, the less a chance of exploding one time, but the more times you take that chance. So let's do some math. So let's try to figure out, if the bomb is in the box, what is the probability that there's any explosion, that over the whole course of the experiment, do we ever explode? And this is the probability that we explode at time 1, or that we explode at time 2, or that we explode at time 3, and so forth. And you can therefore say that it's at most the probability of exploding at time 1, plus the probability of exploding at time 2, plus ... the probability of exploding at time n. And this is like the union bound, as they say, in probability. And now each of these events or occurrences is basically the same because, every time step that the algorithm goes through, in the bomb case, the same thing is happening. You're taking a photon at angle theta, putting it through the horizontal filter, and, hoping that you don't explode. So all of these probabilities are actually the same. It's just the probability of exploding when you put an angle theta photon through a horizontal filter attached to a bomb. So this probability is just, or the sum of probabilities is just n times the probability of exploding in, one of these attempts. Okay, so you see this is getting bigger the bigger n is, but let's think about now the probability of an explosion. Well, let's go back to this picture of what a qubit polarization state can look like. So the photon state that we're putting into the filter is at some small angle theta. So maybe this is a picture of its state. It has most of its amount on 0, or most of its amplitude on 0, and only a little bit of amount on 1. And in fact, you might recall exactly the amounts it has on 0 and exactly the amounts it has on 1. So this, the first coordinate of this yellow vector, or the x-coordinate of this yellow vector, is exactly cosine of theta. And the y-coordinate, or the height of this yellow vector, is exactly sine theta. So it has cosine theta amount of 0 and sine theta amount of 1. Okay, so if you put such a thing into a readout device, as we saw, the probabilities are the squares of these amounts. So you'll have a cosine theta squared chance of reading out 0, and a sine theta squared chance of reading out 1. And it's the 1 where, the filter blocks it and turns it into heat and you explode. So the probability of getting an explosion in one of these passes, one of these iterations, is exactly sine theta squared. Okay, so now we have to do a little bit more math. Let's zoom in a little bit here, just so that we can recall a basic fact of geometry. So this black height here is sine theta. Exactly, this is the y-coordinate of this yellow vector. It's this side length of this triangle. Remember, this is a unit circle here, so the length of the yellow vector is 1. On the other hand, this arc length, this pinky purpley arc length here, is exactly theta, and this is because theta is in radians. Okay, so actually, sort of by definition of radians, if this angle is theta radians, it exactly means that the length of this arc here is theta. And I only draw all this to, point out that, you can see that the length of this arc is longer than the length of this black height. So I draw this picture just to illustrate the fact that theta is always bigger than sine theta. And I'm going to use that fact over here in this little inequality to just say that sine theta is smaller than theta. So I can say that this probability of exploding at all is at most n times theta squared. It's at most this. And this is a nice expression because we know exactly what theta is. Theta, if you recall, was 90 degrees, or pi over 2 radians divided by n. So when we plug this value into this expression, we get n times the square of pi over 2 over n. And now you can finally see the trade-off that happens with n is kind of interesting. These n's don't cancel each other out, for example. This n only cancels out one of these factors of n, so we still have an n in the denominator. Okay, so this expression is actually equal to pi squared over 4 divided by n. Okay, and as we all know, pi squared is around 10, and 10 over 4 is 2.5. So we can finally say this is at most 2.5 divided by n. So this is the final takeaway here. The probability that you explode at all is at most 2.5 divided by n. And you see that's actually great in terms of your safety, because the bigger, you can take n to be as big as you want. So the bigger and bigger you make n, the smaller your chance of exploding. So if you take n to be 100, we see that there's at most a 2.5% chance of exploding. And if you take n to be 1,000, there's at most a 0.25% chance of exploding. If you take n to be 1,000,000, there's a correspondingly less chance you'll explode. So that's great. You can decrease the probability of you exploding as much as you want, and when you don't explode, you get the correct answer of the algorithm. You detect whether or not there was a bomb in the box. So this is the summary, and you see it's pretty awesome. It's like, this is the cool algorithm. You can make the probability of exploding as small as you want, and if you don't explode, you get the correct answer without opening up the box as to whether the box contained a bomb or the box was empty. And what you've really done here is you've traded time for safety. So by increasing n, you become safer and safer, but the whole experiment takes more and more running time, if you will, in the language of computer science. Okay, so that's the end of the main story I wanted to tell you. That's the Elitzur Vaidman Bomb algorithm. And I hope it illustrates to you that you can do some kind of interesting computation even with just 1 qubit. Now, if I'm completely honest, this is not really a computation per se. It sort of is, and we saw it as an algorithm, but it's a bit more like a party trick, really. But I like to explain it because it shows off the power and the interesting mystery of quantum computing in a simple setting with just 1 qubit. And it's really quite similar to more interesting and more powerful algorithms that do exist on quantum computers. For example, this algorithm, Elitzur Vaidman Bomb algorithm, is quite similar to something called Grover's algorithm, which is a more sophisticated algorithm you can do with multiple qubits, which, well, it's a really cool algorithm. It can solve a problem quadratically more efficiently on a quantum computer than it can be done on a classical computer. And indeed, the real coolness of quantum computing will come once we can build quantum computers, which are, like these devices we saw with, the photons and the mirrors and the slabs that can manipulate thousands of qubits. So in fact, it's not hard to manipulate 1,000 qubits. First of all, it's not hard to get 1,000 photons together. And it's also not hard to manipulate them in isolation. But to do really cool quantum computing, you have to do something trickier. You have to do operations that involve more than 1 qubit or more than 1 photon at the same time. And this is kind of hard to engineer. In principle, it's possible to build gadgets that will take in 2 photons and manipulate them in a more sophisticated way, depending on how each of them, let's say, is polarized or how they're jointly polarized. But this takes a little bit more engineering, which is why we don't have quantum computers that are actually working these days. But we can build such devices that have, well, 2 or 4 or 5 or 10 or maybe 50 qubits right now. And if we can get this going with thousands of qubits, we can get really, really cool computations. Let me just end by explaining why it's so incredibly powerful if you could get 1,000 qubits together and manipulate them in superposition. So if you remember, if you have one qubit or one photon, it's sort of defined by two numbers, x and y, the amount on 0 and the amount on 1. Now actually, if you have two photons together, like, their basic states, there are four of them. They can be 0, 0, 0, 1, 1, 0, or 1, 1. So the basic possibilities are they're both horizontal, they're both vertical, one's horizontal and the other's vertical, or the other way around. But quantum mechanics tells us we can have like any kind of superposition or amount of each of these four possibilities. So actually, the true polarization state of two photons is defined by four numbers, x, y, z, and w. And if you have three photons, their true state is defined by 8 numbers, because there are 8 possibilities for 3, 0, 1 bits. And if you have 4 photons, their state is defined by 16 numbers. If you have 5 photons, their state is defined by 32 numbers. And if you have 1,000 photons, then their state is defined by 2 to the power of 1,000 numbers, which is a colossal amount of numbers. This is more numbers than there are, atoms in the universe. So there's a tremendous amount of potential data can be stored using just 1,000 photons. Now, the reason quantum computing is interesting and it's not all-powerful is it's a little bit tricky to manipulate these numbers and to build physical devices that change these numbers in a way that corresponds to doing a computation. We could have a dream that, like, if you manipulate these 1,000 photons just right, you can cause nature to do some really interesting computation on the 2 to the power 1,000 numbers that encodes their state. Not quite so easy, though, because this has to be arranged very carefully, and also you cannot just look at the photons and see what these numbers are. In the same way, when we had just one photon, you can't just look at a photon and tell what that angle theta was. You can only put it into a measuring device and get some probabilistic information about what that angle was. And in a similar way, if you have 1,000 photons, their state is defined by 2 to the power 1,000 numbers, but you can only learn some probabilistic information about those numbers by measuring them. So, designing quantum algorithms for 1,000 qubits is a more sophisticated business, but you can tap into this power potentially to do some amazing things. So we can just imagine what the possibilities will be if you could harness this computational power of 1,000 photons or 2 to the power 1,000 numbers.